Bismillahirrahmanirrahim. Good afternoon, everyone. Our lecture today will talk about the second kind of doping semiconductor. Let me prepare this. Yes, let's start. At first, let's definition what does mean in type doping. It is one type of two kinds of doping. It is very small amount of a group 5. Here the situation will be different. At the P type, we was dealing with elements belong to group 3. Here the elements dealing with another element belong to group 5. Let's discuss what that means small amount. That's mean we have too much numbers of silicon atoms, and we will put one atom belong to these 5 electrons at the last shell as the last orbit, like arsenic or phosphorus. By this situation, we will protect and save this wall, this big atoms be clear, but with small, little bit different. And how we will can dealing with this difficult, how can take benefits from this process. Now let's complete, like I said before, here we dealing from another elements. 5 has 5 electrons at the last orbit, like arsenic or phosphorus. Here let's conclusion, this arsenic atom, like I said before, has 5 electrons at the last orbit. Like I said before, silicon has 4 electrons at the last orbit. That means 4 legs. And let's say silicon, like animal, can't walk or running without these 4 legs. Because here, like I said before, these 4 legs help this atom to reach satisfying situation. But our problem here is different. Here, arsenic has 5 electrons, and just he need 4 electrons to can prepare, to can create 4 covalent band to can catch the others neighbors, the 4 neighbors from the 4 sides to can create its great wall. We can say this preparing atoms like wall, okay? By will catch each other by 4 electrons by using this 4 covalent band. Okay, I'm sorry, I forget to draw this 4th line to can explain very well the 4 equivalent band from fourth side. Okay, in equivalent band, the 5th electron has no place in equivalent band. Like I say, this is our problem, and how the phosphor atom will can dealing with this problem, because that will give and lose it to be positively charged. Why? In this situation, this atom be positively charged, not negatively charged at N type. Here, positively charged because actually the phosphor atom donate or send 1 electron to can reach the comfortable situation to can catch the another 4 silicon atoms from 4 sides to gonna create its wall, okay, by sending 1 electron. By this situation, he lose minus electron, he lose minus he lose charge electron charge, and like we know, electron charge is minus, is negatively, because that the situation will be positively charged, because the arsenic losing one electron from his last shell. Therefore, a Coulombic attractive force between electron and arsenic ion must be overcome. That means there's something like discussion, no way, must be overcome. Now let's focus on this important differentiation, donor atom. It is, what is meaning of donor atom? It is a foreign atom as of group 5 electron, not 3 like the last lecture, has 5 electron, and the last orbit can donate its 5th electron to the neighbor silicon atom. That's mean at the twice situation, if we're dealing with p-type or if we're dealing with n-type. Then the atom arsenic or phosphor or boron will dealing with other neighbors to can solve his problem by send electron or take electron to can reach the satisfying situation. Let's discuss this important question, why the electron at this process is potential energy. Because like we know, we have two charges separated from each other. One of them is arsenic ion, and the second is electron, the fifth electron. The second is the fifth electron, yes. If the electron separated will be in the first orbit and going to be potential energy. Okay, we must focus on this last line in my opinion, because the fifth electron separated will be in the first orbit and going to be potential energy. Now let's focus on this simple function, simple important function, because this function, like I said at the last lecture, we can calculate the concentration of holes or concentration of electrons in p-type or n-type doping. Here, like we say, we discussing the important thing in n-type, because here n-type doping, that's mean we know the concentration of electron directly, because n here concentration of electron equal the density of effective donor atoms directly. Okay, by know the concentration of electrons equal nd, that's mean concentration of holes will equal the square intrinsic divided on concentration of electron, or we can say divided on the density or effective donor atoms. ND, that's mean it is the density of effective donor atoms. Here, let's focus on this question, why the density of a state effective mass is different from conductivity effective mass. We will discuss this question at the last this lecture. Here, let's focus on this note. Donor atoms will have energy level ED in the energy band gap below the EC. Here, like I said at the last lecture, at the diagram, let me show the diagram. Here, EV, the valence energy band, at the last line here, and the up point, the up line will show the conduction energy band, and between these two lines will be energy band gap. Here is created, ED is created inside the energy band gap. Like we know, ED, that's mean donor energy band. But we have condition like in p-type doping ED must be near from condition energy band. And like we see here, we don't have acceptor energy band, because here we discussed the more important information about n-type doping. If you put here EA inside this diagram, that means you couldn't understand anything, and you couldn't understand the important information between these two situations. Okay, now let's come back here. Like I said, the conduction energy band and valence energy band are due to generate silicon by itself. So in valence band and conduction band, they can't energy level belong to this arsenic atom or donor atoms. Therefore, donor atoms are creating energy inside EG. The most important line here, the last one, donor atoms are creating energy inside the energy band gap, like the last lecture when was EA acceptor, energy acceptor atoms are created. Energy creating inside the energy band gap. But here, sure, some difference, because EA was low, near from EV here, it was here, near from valence band, but here in n-type doping, donor energy will be near from EC, and the electrons will try to jump from donor electron band to conduction energy band, like this, like the diagram illustrated to us. Okay, let me complete. Now, why the donor atoms have energy level in the EG just below the EC band? This important question. This fact, okay, we know it now, but let's know why. Because arsenic atom give 1 electron, like I said before, because have 5 electrons at the last orbit, and he will attempt to send one of them to can reach comfortably situation and can build its wall with the other's neighbor. 2 crystal energy. After that, electron from arsenic atom jump, like this illustrated, this diagram illustrated to us. This electron tried to jump to the conduction band, energy band. Okay, this is very important. Here, we must note that the impurity atom. What does mean, the impurity atom? The impurity atom here, that mean donors. And the impurity atom at the p-type, that mean acceptors. The impurity atom here at p at n-type doping donors are not belong to silicon crystal. Sure, because it's something like foreign atoms, something like strange atoms. Try to attack, try to be inside the structure, but at the last didn't belong to the same atom, because all of these elements not silicon at all. The impurity atom are not belong to silicon crystal. They can't occupy energy levels either in the valence band or in the conduction band. Last question here, and after that I will finish this lecture. Why density of a state effective mass is different from conductivity is in some semiconductors? This question was last a few moments, and I said I will discuss it at the last this lecture. How does the density of a state effective mass differ from the density of a state conductivity effective mass? These two questions has the same meaning. Our meaning here has two parts, two reasons. Okay. Why density of state effective mass is different from conductivity effective mass in some semiconductors. Let's answer this question. Reason number one, the band structure of real semiconductor in 3D sure is different and more complicated from the same situation in one dimension. More complex than single parabolic conductive band and valence band. Reason number two, in real energy band structure of silicon, there are 6 different conduction band valence. That's it. Thank you about your attention. Have a good day. Gelecek derste görüşürüz arkadaşlar. Kendinize bakın. Eyvallah. I will dedicate this video to my fiance. Let's stop, share, and that's it.